Thank you, all of you guys, for coming. My name is Antoine Cohade. I've been working at Intel for 3 years now, and I'm gaming application engineer, so my job is to work together with game developers to help them optimize their games on Intel hardware and make them to a better experience. You'll regret it. No, stay on the floor. I need to tell my manager there were some people sitting on the floor during my talk. Anyways, and where was I? Oh yeah, I've been looking for power and power optimization for a while now, even before working at Intel. Actually, I started in 2006 or something. I was back then a student, just bought myself a brand new laptop, Core to Duo, NVIDIA graphics, etc. It was one of the first ones claiming 8 hours battery life. I was super excited. I just get first day of class. I was bored. I started playing the best game ever, Age of Empires 2. And I was extremely upset when after 2 hours I ran out of battery and had to follow the class for the whole day. And so that's when I started realizing, and I looked more into it, and I realized the hardware can be as good as it wants. If the software is taking all of the power available, the battery life is going to suck. All right. Yeah. So, yeah, you can. I'll post the slides online so that you can read that one. It's not interested, but I had to put it there. Yeah, the clip is not working. So, agenda for today: we're going to see why power matters. We're going to see a bit how power works on current generation hardware. And then probably the most interesting part for you guys, how to optimize your game. And we're going to show you what the guys at Funcom did on Lego to optimize their title. So after the first topic, why power matters. You guys can read. When I was putting that talk together, I spent 30 minutes on the Play Store looking for, I just Googled for, look for battery. And I got those testimonials. I'm pretty sure none of you really want to have that kind of comments in your game. Just raise your hand if I'm wrong. But and yeah, the users are becoming power aware. They want to be able to play their games on mobile or on laptop for many hours without running out of battery and without having to charge their devices. Now it's all about, whenever you buy a device, hey, does it run the whole day? Well, if you're playing games and it sucks the battery, people might just simply stop playing your game. Second reason, and it's already more technical. So basically on integrated graphics, which is more than 80% of the graphics card sold at the moment, the CPU and the GPU are sharing the same power envelope. And that means that even if you feel like you're limited by the GPU, the CPU is actually impacting the GPU performance. So we created a small workload that was showing that. The workload is just synthetic, and it's really GPU limited, rendering some fractals on the GPU side. And we are running some heavy kernels on the CPU that are not related to graphics at all. And what you can see in former graphics, discrete graphics, is that the frame rate doesn't change at all, of course, because it doesn't impact, the CPU doesn't impact the GPU. On the other hand, on integrated graphics, which is what you get now on laptops and mobile platforms, as you can see, whenever you add one CPU thread, the CPU is going to require more power, taking power away from the GPU. So what's happening in that case is that the frame rate is going to drop because CPU is going to take power away from the GPU, and the GPU won't be able to run at its maximum frequency, and that's going to drop the frame rate significantly, in that case more than 20%. And lastly, devices have varying power behaviors, and that's something you don't control. OEMs are able to change the power behaviors depending on any factor. That's, in this example, it was one of these nice 2-in-1 devices. And basically, when it was in laptop mode, you could use up to 15 watts. And as soon as you flip it to tablet mode, it was only using 10 watts. Well, if your game is running fine at 15 watts, it might not be running great at 10. And there's lots of examples right now of like devices that are thermally throttled, etc., etc. And for you, having your game power optimized from the beginning would allow you to avoid being impacted by that kind of behavior. So the second topic, I had a really long part and quite deep technical. I tried to summarize it in one slide. Basically, it's how does the hardware is handling power at the moment. So each component of your SoC has a sleep state. So basically, when your component is active, it's going to be in C0, and if you go to sleep, you're going to go into deeper sleep state, and you're going to save power by going to sleep. And it's the same thing when you're active. You have performance states, and the more you require, the higher the state is going to be, and the more power you're going to consume. So these two parts literally means that if you want to save power, you have to do less, or do the same amount of work, but more efficiently. And finally, a point that's really important is that the overall package power is determined by the highest of all of the C state. So let's say you want to save power, you're going to do lots of optimization on the GPU side. But if your CPU is preventing the overall system to go to sleep, then it's going to prevent the overall system to actually save power. That's why it's not only about optimizing CPU or GPU. You need to optimize the overall package in order to have some power saving. So now for you guys, probably the most interesting part. So how to optimize your game? Well, the rule number one is to adapt to your platforms. I mean, there are numerous processors and platforms with different memory frequencies, with different memory size, frequencies, screen size, etc., etc. And it's really, really hard to have a game that's running on all of those platforms and that is optimized for all of those platforms. So the best practice here is really to take those factors into account and build some performance bins. And so for those who are not familiar with those performance bins, the way to do it is either you run some small snippet of your game when you're loading the game, or you're going to just use a GPU detect sample, so you just detect what kind of GPU you're running on. And depending on those factors, you're just going to select the best trade-off between visual quality, power, and performance. I mean, isn't it annoying when you're just starting a new game and it's like running at 2 FPS and you are not able to even change the settings? That's the kind of experience you would have without doing it. So that's basically the way you should just always try to, when you start your game, to build those performance bins. So the second point is, I mean, I told you if you want to save power, you need to do less work. Well, one way of doing less work is to simply cap the frame rate. I put the lines of codes that does that. It's literally one line of code on Intel hardware. And for you guys in Unity, it's even easier. It's just like one checkbox. So there's two ways of doing that. Either you just do the checkbox and you cap with vsyncs at 30 FPS, or you can use the target frame rate command line script that just does that for you. And you can see that you're doing twice less work, and performance-wise, you can get some pretty big performance benefits. So those are just like 4 games I tested before capping the frame rate and after capping the frame rate. And of some of them, you can get up to like 180% battery life increase, so almost twice already, just simply by doing that. playtime. And for those of you who, and I know there's lots of games, that casual games, that actually don't even, that if you're not moving, for instance, don't even need to re-render the whole frame every time. If your scene is static, why not simply capping the frame rate at 15 FPS or even lower and re-rendering whenever the user is actually touching the screen or doing some action, so that you would, whenever nothing is happening, you would actually go really, really into deeper C state and save a lot of power. Another way to look at power, it's the energy that is required to render each frame. In that case, I did this test on last year, and basically you just, for each of those resolution, I measured the energy that was required per frame. And you can see that when going from 800 by 600 to 16 by 9, you're actually doubling the energy required per frame. I mean, I'm not going to tell you to run your game at 600 by 800, but especially on the mobile world, where you get some like devices, tablets that have 2K or 4K resolutions, it's, to me, ridiculous to run games at that resolution. It's a huge waste of power for something your user is probably not able to see. So in Unity, you can simply do that. In order, a little trick that I use in order to have the impression of a good visual quality, we're still rendering at a lower resolution, and that's now available with the GDC in the Unity personal edition as well. You can render to a smaller render target, and then upscale that little texture that you have into full screen and add the UI on top of it. So you're going to have a really full-size resolution UI, which looks really sharp, which is what the user is going to look at, and still saving power and having decent 3D quality. So if computing data is taking a lot of power, moving data around is also using more power than people thought. And I mean, just as a quick example, if you're running your game at 60 FPS on a 2K display, just rendering once your frame buffer is going to use 1 gigabit per second. Currently on laptops, the maximum, the limit is approximately on, well, if you have 2 memory DIMMs, it's only 20 gigabit per second. And you're going to tell me, when you look at the power savings that you can get here on the left side, okay, you're going from 0.8 watt to 0.5 watt. It's not much. Of course it's not much if you're running on a desktop, etc. But if you're running on a tablet is not like the CPU is only consuming 2 to 3 watts. And in that case, saving half a watt or even less is making a significant difference. And so just a simple way of doing it is just, for instance, changing the render target format, and you can help saving 15 to 20% of power. Be careful with spin loops. So that's a general rule for every developer. In Unity, most of the stuff has already been optimized. We've been working really close with some of the Unity engineers in order to save power. But basically, when you're doing spin loops to pull, or like for thread pulls, or like to reduce the input latency, etc., this is preventing the CPU and the whole system to go to sleep, which I was talking earlier today. And avoid that. You really need to avoid that as much as possible. And one way of avoiding that is to use the pause instruction into a spin loop in order to hint the CPU that this is a spin loop. Don't just spin as fast as you can. You can go to sleep in between each loops. Originally, when I planned that talk, I thought I would have an hour. So I summarized a bit more all of the important things I wanted to talk about today. So handle the loss of focus. Something you might not know, but when you do Alt-Tab or Windows-D on your laptop or desktop, even if you're not seeing anything, you still keep on re-rendering everything you're doing, which is a bit sad knowing that nobody is seeing it. So there is a way to detect that you're not actually in full screen, and you should, of course, put your game in pause and stop rendering in that case. Color buffer clears. So some people have the tendency to add a lot of clears just always to make sure that the buffer is clean. Well, in the case where the clears are not optimized in hardware, it takes up to 1 millisecond just simply to do one clear on the frame buffer. So there are optimized clears in hardware. One of the ways to do that is either to use a black color or white color and not like some fancy pink. And in lots of cases, actually, especially for 2D games where you have a full screen pass on top of it, or like apply a texture in the background, your clear is not even necessary. And you can just simply save, that's like general optimization, simply save 1 millisecond simply by doing that. 2D games optimization using depth, that's a bit more technical, but like let's say, let's take the Candy Crush example. When you have, well, there's only a small part of the frame that's actually changing every frame. The rest, there is like a border around that's not changing every frame. So why would you re-render that part every frame to add that part on top of it? So one way of doing this, even with 2D games, is to use is to fill a depth buffer from the beginning, so that basically for every frame, that part of the depth buffer is still on top, so it's not re-rendered every time, and you simply re-render the part of the screen that's changing. CPU activity, I mentioned it earlier today. It's important to pay attention of what you're doing in the CPU, especially sound system. I've seen some amazing examples of games where people were using physics to simulate the echo in a tunnel. That might sound great on your 11.1 sound system, but when you're playing in the subway with your speakers, you probably won't hear any difference. So that's the kind of stuff you can pay attention to, and especially when you're running low on battery, disable. And the latest one is the use of next-gen APIs, DX12, Vulkan, Metal, etc., etc. Those are great. They completely reduce the CPU overhead. And you can actually, we've already run some tests. We have a demo actually in the show floor where you can see that DX12 on the sample we're showing is using half the power of DX11 for the exact same scene. So just come and visit us later. There is also a talk right after from AMD about DX12. So as soon as it releases, you can just use that and save a lot of power and optimization pretty fast. Now let's have a look at Lego and what the Funcom developers did. So just to be introduction for those who don't know Funcom, it's an Oslo-based studio. Their two big previous games were Age of Conan and The Secret World, and they were like hardcore games for hardcore gamers, you requiring a desktop PC to play, etc., etc. And they wanted to have like stunning visual qualities, but basically they realized last year that they didn't have enough market share, and that there was only a few people that were able to play the games. So with Lego Minifigures, they actually completely changed their target. So it's a game aimed for kids, and they like to play on tablets and on multiple devices the same game. So they have the game scaling from the smartphone world to the PC world. They had to create, so it's not a Unity game, but they had to create a new engine. And they still like high-end features. So basically, they simply did it, is they designed their games, and they targeted the smartphone world, and then so that they made sure that it was running, and then they added on top of it additional features in order to have it look amazing. You'll see a couple of screenshots in a few slides. So what they've done, that's basically the list of features they've done to save power. So capping the frame rate, lower the visual quality of the lighting, the filtering, and some post-processing effect. So the first one it's basically capping the frame rate at 30 FPS. So in order to, so on some devices, using simply the VSync at 30 FPS and sync every 2V blank wasn't working. So what they did is essentially they did CPU frame capping, which is similar to the setting the target frame rate in Unity. And as you can see, you have pretty good results. Just simply, the CPU power is saving 35%, memory 25%, and overall system, so measured at the battery level, was saving already 25% simply by doing that. Second one is that they use lower quality shadows, so they lower the resolution of the shadow maps, they did simple filtering, and they disable AVSM. AVSM is a rendering technique that allows you to do real shadows on see-through alpha particles, and that looked great. And they had some small additional power saving in there. So that's what the game looks like with everything turned on at the maximum visual quality. So here you can see there's some pretty good, pretty realistic shadows going through the smoke, and there's also some smoke on the floor some shadow on the floor from the smoke. Sorry. And this is what it looks like when disabled. So as you can see, the smoke is still there, but it doesn't look as good, and they have removed some. You see that there is no shadow on the floor anymore from that cloud. So they were still unhappy with it, so they decided to go even further. They simplified their lighting model, and they actually simplified the shadow map quite a lot, so that only dynamic objects were shadowed. And that actually still looks good because, well, the shadow is important on the dynamic object mostly. And here they had some significant savings, again, up to 10% at the system power. So what it looks like here, that was the exact same screenshot I showed you right before, and when they disable it, they simplify. So they, of course, it doesn't look as good. They remove some of the shadows, but you still have the shadow of the bee, etc. So when it moves, it still looks quite realistic. And lastly, in order to go even further, they disable all of the post-processing effects, so depth of field, gut rays, anti-aliasing, etc. And what it looks like is, you can probably see, the best you can see is in the background, the sea. You're going to see that it's going to get sharper as the depth of field get disabled. So that's what the game looks like after all of the power savings they've been implementing. And the final result is that when we measured, so we did battery random tests. We just like charge the system maximum, we enable power saving, and we just let it run until there's no battery, and in both cases. And you can see, I mean, there are some small differences between the two frames, but it's still a playable game, and people still can have fun playing with it. But as you can see on the battery lifetime, you go from on the second system with integrated graphics, you go from 2 hours to almost 4 hours. So you, in that case, actually doubling battery life by doing some simple modifications. So what's important is that it's not that everyone wants to have lower quality. Some people still want to play the games on desktop and still want to burn power and still want to enjoy the best visual quality. But what user wants, I think, is to have the choice. If they want to be able to play in the subway with the power saving mode, they can. If they're at home and want to play with the maximum visual quality, they can as well. And so what Funcom did in their game is that they added the possibility to enable or disable that power saving mode, in addition of detecting when the battery was low or when it was unplugged. And yeah, to conclude today, so users cares about battery life. You've seen the first testimonials they were showing. They want to be able to play their games for a couple of hours without running out of battery. And second point is that power optimization is performance optimization. I mean, you guys are already doing that in order to have your games playable on every platform you want to have it. Just do it a bit further and have that power saving mode that can make your user happy. And as you can see, just doing the right thing and the right optimization can bring terrific battery gain, and in the case of Funcom, doubling the battery life on laptops. If you have any question, I think we have a couple minutes, 2 or 3 minutes. Otherwise, I'll be today and tomorrow on the Intel booth and showing DX12 and a couple of other cool features.